In the previous lecture, I put forth the empirical evidence that nature is remarkably similar across scales and scopes. All data display essentially the same patterns: skewed distributions, sigmoidal curves, logarithmic spirals, power laws, all of which is coined as the grand regularity. So we cannot tell, when without legends and units on the axis, from where the data comes. It's not nature, but we who invent the labels, set up the categories, and define the units of measure. Whereas the universe is one ever since the dawn of time. Since the ubiquitous patterns, the grand regularity, emerges with time, we need to answer the profound question, what is time? To explain what we observe. The flow of time is one of the most mundane matters, yet it's a big problem for physics. While we experience time to have a direction, the laws of physics as we know them today do not make a difference whether time flows from the past to the future or from the future to the past. So, where does the arrow of time come from? Asked Arthur Eddington, the English astrophysicist who became famous for measuring that a beam of light bends in the sun's gravity as predicted by Albert Einstein. Theoretically speaking, everybody in the universe is immersed in space-time. Yet general relativity explains neither the substance of space nor the flow of time. So there is a serious lacuna in our learning, given that history is on display everywhere. Of all obstacles to a thoroughly penetrating account of existence, none looms up more dismayingly than time, wrote John Wheeler, a well-known physicist, a great figure of the bygone golden age of general relativity. So, let us first clarify the nature of this problem for physicists and then focus on expressing our unproblematic everyday experience of time using the concepts of physics. This is how Galileo structured observations as mathematical laws. Let us recall that more than 100 years ago, physicists encountered difficulties in explaining the results of some simple experiments with their usual methods, which are now called classical physics. These conceptual problems led to modern physics. Today, we have another issue. Although calculations do match the measurements, we do not understand how equations correspond to reality. This paradox is at the heart of the whole trouble with modern physics. In general relativity, as well as in quantum mechanics, the flow of time is without cause, so there are no consequences either. Bodies move along their optimal paths, planets orbit the sun one cycle after another, comets come and go. Within modern physics, it does not even make sense to ask why things happen. There are no causes, no consequences. Such a view of the world is strange. We don't understand any effect without some cause. In fact, the central tenet of science itself is that every single phenomenon in the universe can be shown to have a natural cause. Since the flow of time is a natural phenomenon, it seems reasonable that it too should be shown to have a natural cause. Einstein's famous slogan, "God does not play dice," captures the foolishness of a belief that any consequence could be the result of a mere chance without any proximate cause. The mystery of time has only deepened since the early 20th century. Quantum theory is not bounded by the microcosm of particles, but leads logically to the existence of parallel universes. If you take the theory seriously, then your worldview is inevitably remote to the reality we know from our own experience. However, we cannot present any evidence of a parallel reality. If the theory cannot be put to the test, does it qualify as science? On the other hand, if you abandon quantum mechanics as absurd, how would you then calculate the results of some simple experiments? For the physicist, it was out of question to discard this productive, even if a strange way of doing science, known as instrumentalism. It has no ambition to explain the phenomena, only to model data after the fact. I'd say we cannot high-handedly label one outcome of modern physics as suitable, such as accurately calculated atomic spectrum, and another unsuitable, such as the multiverse. The oddities must not be ignored, but ought to be illuminated, because our thinking might be wrong, even where we deem our reasoning to be right. We experience the passage of time, whereas a textbook physics states that in the microscopic world of particles, the laws of physics are independent of time's direction. But it's a thin line between a microscopic and macroscopic. So could it simply be so that as long as nothing is happening, time just does not point anywhere? Have physicists just chosen to define the laws of physics to be free from time's arrow? As long as we imagine time without substance, it remains an impenetrable abstraction. Isn't it shocking that we do not understand what time is? After all, causality is at the core of reality. What else do we not understand when we fail to grasp the quiddity of time?
Is time an attribute?
In contemporary physics, time is instrumental, insubstantial, incomprehensible, whereas it should be concrete, causal, and comprehensible. So let us go back to reality and once again use Galileo's method, where one's own experience is structured in scientific terms. When the equation for time cannot be found in textbooks, we must draw understanding from experience. This does not mean discarding the achievements of physics, but rather making sense of them. A clear frosty night under a starry sky is a great experience, except that with time it feels cold. Heat does not escape by itself, but together with time. The observation is obvious, but that's precisely why it's precious. Can we thus infer that the passing of time is always associated with a flow of energy? What is it that moves when energy and time flow? Under a starry firmament, we feel cold because heat escapes from the warm skin to the cold space. This experience exhibits causality. The difference in temperature is the cause, and the loss of heat is the effect. Heat is carried by photons. The photon is a quantum of light, or as Newton said, a corpuscle of light. The human eye is so sensitive that it can register even a single quantum of light. Since we see and sense the quanta of light, we know them through experience. According to Bertrand Russell, the underlying elements of reality must be objects that are known through experience. It is wise to eschew as meaningless, impenetrable concepts that have no connection to our own experience. Clearly, the photon carries energy. But does the photon carry time too? This is an essential question. The union between time and energy is really a matter of everyday life. It's apparent, for example, at sea, when a heavy swell first lifts and then drops the boat. This happens over the wave's intrinsic period of time. Likewise, the photon carries energy on its period. Thus, sunlight does not bring about a change as energy alone, but also as time. The photon's wavelength that carries energy on its period, and so on. The photon propagates, and time and energy moves. Energy and period are inseparable properties of a photon, as Max Planck exposed in 1900. The fame following this great discovery did not make Planck haughty. Though the equation works, he admitted not to understanding the meaning of a constant that the spectrum of light exposed. The photon energy can be calculated by multiplying the frequency of oscillation corresponding to the color of light by Planck's constant. This E equals FH is among the most important equations of physics. But what does it mean? The frequency indicates how many periods fit in 1 second. Since the period of visible light is so short, there are 100 trillion periods in 1 second. The period is very short, but not naught. So time is indeed real. It is a property of the photon-like energy. To regard time as the period of light quantum is a new viewpoint. It's not a new finding. In fact, the second is defined as the fixed number of multiple periods of the photons. So time is not illusory, but factual, even visible, since the period of the red photon is longer than that of a blue one. This seemingly trivial conclusion about the substance of time will lead to a significant change in the worldview, as envisioned by Ludwig Wittgenstein. He said, "The problems are solved not by giving a new information, but by arranging what we have always known." According to the new view, time and energy do not exist as such. There is no energy as such, but in the form of radiation and matter. There is no time as such either, but always in the form of a period. Time is as concrete of an attribute of the quantum as energy. As the quanta move, both energy and time flow. Planck constant is equal to energy multiplied by time. This rearranged equation, H equals ET, is mathematically equivalent to the one in the textbook, but the meaning is different. Here, Planck's constant is not just a coefficient of proportionality, but the measure of the photon. Rather than through experience or experiment, Planck found the constant by interlacing two equations together. While covering the whole spectrum, the two branches, the low and high energy bands, Planck's law of radiation does not actually explain the light. Planck was therefore blind to the essence of light. The photon energy decreases as its period increases. However, the energy cannot drop to zero, and the period cannot extend to infinity. If this were possible, the photon would vanish. But Planck's constant means that the quantum is indivisible and eternal constituent. This inference is a solid foundation on which we can build a coherent and comprehensible worldview. We understand as well that no system can have a zero energy because there is no system without any quantum, that is, of any constituents. Not even the empty space, as 1 cubic meter of it holds the energy of about 1 billionth of a joule. The void is thus not just a geometric space. It is some sort of a substance embodying energy and time, that is, quanta. The postulate that everything comprises quanta of light, the photons, transforms our outlook on reality into a thoroughly tangible worldview. As Francis Bacon advised, it is in vain to expect any great progress in the sciences by superinducing or ingrafting of a new matters upon old. An instauration must be made from the very foundations if we do not wish to revolve forever in a circle, making some slight or contemptible progress. A system is static when quanta move neither in nor out, but circulate on and on. Nothing happens. Quantum mechanics works well only at this balance, but an event, say an observation, is expressed with impenetrable jargon, where the wave function, so to say, collapses. One of the superposed states will then become instantly observable, but which of them will be determined by pure chance. That's a miracle. The idea that the fundamental element of time is the period of a quantum is perhaps surprising in its simplicity. There is no more of a mystery hidden in time than in energy. Time and energy are complementary properties, as the founder of quantum mechanics, Niels Bohr, said. One cannot be without the other. When the energy of the photon decreases, the period increases. Nonetheless, light quantum maintains its size per Planck's constant. Energy and time change hand in hand also when the quantum takes off from a flashlight into the sky, as the wavelength of light dashes away from the Earth's gravity into space. its energy lessens and its period lengthens. Its color shifts toward red, albeit only slightly. Earth's gravitational field is hardly denser than that of a free space. In a constant vacuum, light does not age. However, the light that departed from the blazing early universe and arrived at the cold present has extended so much that our eyes cannot detect it. But our body can still feel it. The night sky is cold and dark because the average temperature of the expanding universe has fallen to less than 3 degrees above the absolute zero. This massive change in energy took eons, about 14 billion years. The universe could not be expanding unless the photon period was increasing and energy decreasing. Since time and energy, as well as momentum and wavelength, are complementary properties, the steps in a sequence of events are not interchangeable. Mathematically speaking, they are non-commutative. This means that the outcome depends on the order of operations. For example, a measurement of a particle velocity will change the velocity and thereby affect the subsequent measurement of a particle position, and vice versa. The order of time is the order in which quanta flow.
Why is time relative?
Although Einstein realized that the time is relative, he did not clue us into what time is. General relativity does not even aim at explaining why clocks run at different rates at different places. It only reproduces the data. For instance, the clock up in the attic runs faster than the one in the basement. The difference is minimal, but it has been measured so precisely that there is no doubt about its validity. Since quanta carry both time and energy, we understand that the passage of time in the attic is faster than in the basement, because in the attic, the energy difference, the imbalance between the clock and the surrounding, is bigger than in the basement. Since the gravitational field decreases upward, a clock running in the attic gives away its quanta faster than the one in the basement. This experience-based comprehension of the passage of time is mathematically consistent with general relativity. The calculation is just as it should be. Only our interpretations are revised. Since energy is relative to the surroundings, so is time. Now we have reached a milestone. The mystery of time has been solved. We have found the motive force. An imbalance of any kind forces the quanta in motion. Because the quanta carry both time and energy, the flow of time is the flow of quanta. To decrease the imbalance as soon as possible, the flows of quanta naturally select the path of least time. This is the principle of least time. Now we can also comprehend why the clock runs more slowly in motion than when at standstill. This prediction was verified elegantly in the early 1970s by the physics professor Joseph Hafele and the astronomer Richard Keating, who spent their research grants on the round-the-world fairs. To be on the safe side, they took flights in both directions, east and west. Tickets were also bought for the atomic clock. However, the chronometer was seated affordably to the ticket in the economy class. At the end of the flight, the clock on the eastward bound jet was found to be ahead and the westward bound to be behind the reference clock that stayed on the eastward rotating ground of the Earth. The amount of time gained or lost on the fly, along or against the Earth's rotation, was as much as had been calculated before, and along these lines, Bruno Rossi and David Hall also showed in 1940 that the lifespan of a spontaneously decaying particle increases greatly when the particle moves very fast, almost at the speed of light. However, no particle can attain the speed of light and become uncuttable atomos. Only the photon is indivisible and eternal. Such results convince physicists that the theory of relativity is valid, although it does not explain why the clock runs slower in motion than at rest. Since the clock runs slower in motion than at rest, it must be that in motion the imbalance relative to the surrounding is smaller than when at standstill. If the clock were to move at the speed of light, it would stop. The clock cannot give away any photons when it is in perfect balance with the surrounding vacuum. By the same token, an oar that falls in the river will drift away only if the boat moves more slowly than the stream. So it's logical to ask, is the vacuum, therefore, a stream of light? Well, that is how Maxwell, a leading light of the era, approached the problem. He discovered that the electromagnetic properties of the vacuum determine the speed of light. In 1865, Maxwell wrote that the light is a wave of the void, a ripple, an undulation. Since a wave of water is water, could not the substance of vacuum be the quanta that move at the speed of light?
Why does time move forward?
The preconceived idea that ever-increasing disorder is what directs the arrow of time is deeply rooted in contemporary physics. Our own experience is that it also takes considerable time to put things in order. I would say it takes quite a bit of time to tidy up my garage. To give an example of a common sense realism, we see that an order increases when water freezes, and we see that disorder increases when ice melts. Order, just as disorder, will emerge as the temperature difference between the environment and the different phases of water evens out. It is therefore not an increasing disorder, but an imbalance that directs the arrow of time. When a film is played backward, the course of events looks unreal. Shards of glass on the floor just cannot emerge into a solid face and rise back on the table. For that to happen, work needs to be done. But we see no one doing it. Time does not move forward all by itself. It takes an imbalance for the quanta to move. Boltzmann was impressed by Darwin's proposal of evolution by natural selection, but did not see the need to make a fundamental distinction between the living and non-living. A stream naturally selects its course along the steepest descents for difference in heights of water even out as quickly as possible. Likewise, heat naturally selects an open door rather than a wall for temperature differences to diminish as quickly as possible. Flows of quantum naturally select those paths that lead toward balance in the least time. Time does not just run, it runs in the least time. The principle of least time was known in Persia and Mesopotamia 1,000 years ago. Pierre de Fermat made the Europeans aware of it. Light chooses its way so that time is shortest. The optimal path is called geodetic line. Photons mediate forces through these lines. The photon itself is a piece in the line of force. The optimum of time and energy is one and the same thing because time and energy are inseparable attributes of the quantum. For example, the slightly flattened form of the rotating Earth is energetically optimal, having the least time shape. A clock runs as fast on the North Pole as at the equator. On the one hand, the clock would run faster at the equator than at the pole because the distance to the center of the Earth is longer and hence gravity is weaker. On the other hand, at the equator, the clock would be running slower due to the Earth's rotation. These two opposing effects precisely cancel each other. Boltzmann aimed to formulate the equation of evolution by describing any system in terms of its factors, even without explicitly knowing them. This is possible because when everything is made of the same basic constituents, a generic energy level diagram is valid for all systems, irrespective of complexity. The diagram, in turn, can be expressed using standard procedure of statistical mechanics in terms of probability. Then it only remains to work out a change in probability, and we have the equation of evolution. In short, statistical physics of open systems, the thermodynamic theory of time, if you like, explains processes as flows of quanta. As the quanta carry both energy and time, the irreversible consumption of free energy sets the arrow of time. When this quest for balance in the least time is understood as natural selection, that is, nature selects, evolution incorporates not just the living, but everything. Then we understand that the universe expands everywhere in every direction. Stone falls straight down, a plant grows toward life, and you go for the best price, because in this way, balance is pursued in the shortest time. Gravity, vital force, purchasing power, forces of all forms are what makes things happen. It's a groundbreaking thought that all events, from a nuclear reaction to the expansion of the universe, from a chemical reaction to the evolution of biota, from a small purchase to world trade, are all aspects of the quantized substance moving toward thermodynamically more and more favorable states in the least time. This universal law gives rise to the universal patterns, the grand regularity.
How does time choose its course?
While the quest for balance is universal, we go about attaining it in different ways because different forces influence us. There is no unanimous wisdom. Rather, you are moved only by the forces that pertain you. So it's only natural that my daughter went out with the bloke who captivated her and not with the boy who impressed me. Although the criterion for natural selection is simple, it is not easy to navigate in the choppy seas of diverse forces. Any system keeps evolving until it attains balance of forces, a steady state. Boltzmann understood this superbly, perhaps too well. He did not bother to look for the equation that captures the tendency towards balance, but rather hastened to formalize the equilibrium condition alone. Einstein understood that no one could dictate the balance in advance, but the system itself works its way to it. This insight came too late, for Boltzmann had already taken his own life. Thus, the complete equation of time, where the forces drive the system toward balance, remained unknown until now. The equation engraved on Boltzmann's gravestone in Vienna's Central Cemetery, S equals KB log W, shows that logarithm has been taken of the probability, W, from the German Wahrscheinlichkeit, and multiplied by the Boltzmann's constant KB. The thus obtained entropy, S, an additive measure of its factors, was originally defined without understanding the flow of quanta. So, many aphysicists still today assumes without proof that increasing entropy equates with increasing disorder. By contrast, many a chemist says right away that reactions tend toward balance, where the free energy is at its minimum and entropy at its maximum. Thus, the concept of entropy does not reveal anything more about a causality than does the concept of energy. Entropy increases as energy differences decrease, irrespective whether the course of events results in order or disorder, wealth or famine, joy or pain.
Why is the future unpredictable?
Once upon a time, astronomers amazed citizens and kings by foretelling when a known comet would show up in the sky. The triumph of such a timing went into the heads of the scientists. This rationalist arrogance radiates from the famous quote, "Sir, I have no need of that hypothesis." So Laplace answered when Napoleon asked why he had never mentioned the creator of the universe in his books. The supreme ruler may well have been pleased with the reply, but at the end of the 19th century, the tone changed as doubt snuck in. After all, it turned out to be impossible to predict the orbits of heavenly bodies through eternity. The concern was grave. Will the Earth even stay in its age-old orbit? Gösta Mittag-Leffler cashed in the opportunity. The professor of mathematics, who also served the University of Helsinki for a few years at the end of the 19th century, suggested to the King of Sweden that the problem of three bodies was worth a price. At that time, mathematicians wondered why it seemed impossible to calculate trajectories of Earth, Moon, and Sun forever into the future. Well, complexity makes it hard to predict, but the intermingling of causes with consequences precludes it. The prize went to Henri Poincaré. The French polymath showed that there is no guarantee of stability when the orbits of bodies are open. When energy is changing, time is passing as well. The sought-after calculation cannot be precise until and unless energy is constant. However, the calculation of a closed orbit is not a prediction about the future. In such a system, time does not advance but circulates. The outcome is sort of a paradox. The steady-state equation of motion has the elements of the explanation, but at the point of balance, where nothing happens, there are no causes and consequences to be explained. So, the inevitable conclusion is that the future is genuinely unpredictable, yet bounded by free energy. Nonetheless, in the theories of physics, the desire to predict excludes the fundamentally unpredictable aspects of reality. There is no change without a change in energy and time. For instance, every ecologist knows that when a herd of animals grows, its consumption of environmental resources holds back further growth. Every economist knows that the demand affects supply, whose change will then affect the demand, and so on and so on. Nevertheless, few physicists acknowledge these irrefutable causes and consequences, privileging computable rather than realistic equations. When nothing happens, measurements are precise. That's nice, but out of touch with the real world. Customarily, it is believed that E equals mc squared is an equation of Einstein, but it's a special case of the general formula for kinetic energy mv squared, when velocity v is the speed of light in the vacuum. Gottfried Leibniz and Johann Bernoulli knew of this relation, which the Dutch mathematician and natural philosopher Willem Gravesande confirmed by the experiments in the early 18th century. It was only later that the factor half, familiar from the school books, was placed in the front of the formula to make it solvable, but then flawed. Consider a stone rolling down from a hilltop to have kinetic energy, as is understood, but also the fact that as the stone moves, the landscape also moves. Initially, the stone, which is a part of the landscape, is on the top of the hill, and finally, it is at the bottom of the valley. So the landscape has changed. That change is contained in the original equation about the process of balancing. Whereas the textbook formula, half mv squared, is only about the condition of balance. It is easy to envisage how a stone rolls from the top of a hill down to the valley bottom, but hard to notice, as the stones keep rolling, that the hill levels out and the valley fills up. The landscaping too is in motion as the height difference, the cause of rolling, decreases along with the stone's downward motion. Failing to note this, and one will be led astray. Although the error is small for one stone, a catastrophic discrepancy between the calculation and reality accumulate with time. When mountain has eroded into plateau, stones roll no longer. Although we cannot calculate chains of events precisely, even the earliest events in the universe are not altogether beyond our range of experience, as we feel the cold of the night sky on our skin. The coldness is the relic of the universe's hot creation. So we live amidst all the history that exists. Evolution as a unique process renders the universe asymmetrical in its details. Nevertheless, the constraints of symmetry, that is, stationarity, rather than comprehension of evolving reality, have guided theoretical physics since the mid-18th century. This is both the source of the success and the cause of the crisis that physics finds itself in today. At first glance, one might suppose that if one only knew a system's initial state exactly, then the future could be worked out precisely. However, as is familiar from everyday life, the start of a series of events does not dictate its outcome, because an event will alter the driving forces which in turn will change the course and so forth. The equation of time can be written down, but not solved, because as the quanta move from the environment to the system and vice versa, both will change. History is unique. The American baseball legend Yogi Berra's words strike home. The future ain't what it used to be. The ideal of science is that when one thing changes, others remain intact. However, this ceteris paribus principle, a background-dependent model, so-called effective theory, does not hold. It obscures why things happen. We cannot understand why a stone falls or why our motion continues at the sudden breaking unless we understand that the surrounding void is thereby on its way toward balance. Nor can we grasp the evolution of the biosphere unless we understand that the matter on Earth is thereby on its way toward balance with the sunlight. Nor can we fathom embryonic development unless we acknowledge that the role of the surroundings. Nothing can be changed without altering something else. Consequences give rise to new causes because the flows of quanta from one system to another changes both, as well as their positions relative to the other systems.
What is the meaning of time?
For ages, the vexed question of time has preoccupied scientists and philosophers. The idea that a time is quantum's property, like energy, might be surprising in its simplicity and concreteness. But we would not talk about time if it had no substance at all, and we would not talk about the arrow of time if the substance had no sense of direction as the photon has. Time comprises periods as a trek comprises legs. It's only logical to take the period of a quantum as the fundamental element of time. By contrast, it would be confusing to consider this period and time as different concepts having the same unit of measure as well. Paraphrasing Leibniz, if we do not have the means to distinguish between two things, we must regard them as identical. 100 years ago, this revision of the notion of time, equating it with the period of quantum, would have been a welcomed revival of realism. But today, after the howling success of modern physics, physicists are reluctant to reconsider. How could they have obtained the right results if the grounding of modern physics were wrong? Yet the question ought to be, have researchers got right results? General relativity does not agree with the observations without dark matter and dark energy. Quantum mechanics cannot handle the event of observation. Doubting a well-established theory is a method of searching for the truth as well. However, searching for the truth is no longer the goal of every researcher, as other priorities prevail. John von Neumann, a pioneer in information technology, foresaw this trend more than a half a century ago. He said, "The sciences do not try to explain. They hardly even try to interpret. They mainly make models." Instrumentalism flies in the face of the essential ethos of science. It just generates the right numbers without any intention of explaining the phenomenon. "Shut up and calculate," summarized David Merman on the rationality or irrationality of modern physics in 1989. Time occupied the minds of both Newton and Einstein. Now the issue is neither absolute nor relative time, but tangible time. The quantum is the matter of time. To see what lies in shadows, let us illuminate reality from another angle. Let us look at the whole in terms of details, and the details in terms of the whole. Let us ask what the thermodynamic theory does not explain. The aim is not to justify the net, but to find out whether we understand what we see.